Alright, it's lesson 0.2. We're going to look at functions today with inverses and also graphing adjustments. That's the transformation of graphs you learned in pre-calc 12. Here are some definitions you should also know from your pre-calculus days. The relation is really any set of ordered pairs, so any set of points in the graph. You'll hear this word a lot of function, and it's a special type of relation where for each value of x, there is only one value of y. Okay, and we sometimes use this notation: y is a function of x, or y equals f of x. Notice for all functions, if I draw a vertical line, it should only intersect the function at one particular point. That's why for each x value, there is only one y value. And of course, you've seen these terms before: domain, representing the set of all x values, or independent variables, and the range, representing all the y values, or the dependent variables. So let's look at some examples here, please. I want you to look at examples 1, 2, 3, and 4, and tell me if they are functions of x. Number 1, if you were to graph this out, yeah, remember from our first section, slopes, y-intercepts, yeah, this definitely will be a function. So all lines are functions. Number 2, you might remember this is the equation of the unit circle. And if I ask you to use the vertical line test, look at this. 2 intersection points, so definitely not a function. No way. Y equals negative x squared plus 1. If you visualize what this graph looks like, it's a parabola that opens downwards. All parabolas like this, opening upwards or downwards, are definitely functions. The vertical line test allows you to prove it because it only crosses at one point each time. Number 4 is a little bit interesting. If I were to ask you to solve for y, you'd get something like this. Well, that's y squared. So when I take the square root on both sides, don't forget your plus minus, you'll get something like that. And if I were to actually graph this out for you, you'll see that you have a sideways parabola. Sideways parabola. And definitely, using the vertical line test, no way, not a function. Now, you should also be familiar with function notation. So here I've got two different functions, f of x equals 3x minus 1 and g of x equals x squared. Can you find the following? If I ask you for f of 10, that means for the f function, you replace x with 10. So here's my f of x function. I see x here, so 3 times 10 minus 1. 30 minus 1, 29. Done. Okay, so that's just plugging in the number for x. This time, I'm asking you to use the g function, and this time I'm saying don't plug in a number, but plug in an expression. So wherever you see x, you replace it with that expression. So x plus delta x, all squared. Or if you want to expand this out, x squared plus 2x times delta x plus delta x, all squared. That works too. Now, number 7, this is a function within a function. Yes, hopefully remember this is called a composite function. So notice the f of x function is really 3x minus 1. So in essence, wherever I see x in the g function now, I want to replace it with, 3x minus 1 all squared. Or if you were to expand that out, yep, that's good as well. Now you might not be familiar with this open dot, but this actually is the same thing. It's a composite function, f of g of x. In this case, I will, sneeze first, and then I'll come back and I'll solve this. G of x, once again, is x squared, so the idea here is I want you to replace x with x squared in the f function. And the f function is 3x minus 1. And of course, like I told you, I want to replace x with x squared. So 3x squared minus 1, that looks good to me. Okay. Moving on, let's quickly do some review of domain and range. Oh, yes, number 9. This is a square root function. Hopefully you remember what it looks like. I'll quickly graph it for you, but this is one that got shifted 1 to the right. and the square root function looks like a sideways parabola, so something like this. You can hopefully see that the domain in this case is x is greater or equal to 1, because remember the stuff underneath the square root has to be bigger or equal to 0, so therefore x is greater than 1. And the range, yes, because it's a square root, it has to be non-negative, so bigger or equal to 0. Look at this, g of x. This is like a reciprocal function. Hopefully you visualize what this looks like. You can always use your graphing calculator if you don't remember, but there is an asymptote. That's right, at x equal to 2. So your domain is really x cannot equal to 2, but everything else works. All real numbers. Hopefully you remember the graph looks like this. Whee, whee. Oop, don't cross the asymptote. And hopefully you'll see that the range is pretty much everything except 0. Cool. And for number 11, you can just read it off the graph. So the domain here looks like there are 2 asymptotes, one at 0, so x cannot be 0. X also cannot be 2, but of course all real numbers after that work. And for the range here, interestingly enough, there is some empty space right here. So I'd suggest y is greater or equal to 1. That represents all these values here. And then also, I think y is less than 0. That represents all these values down here. And if you want to write down all real numbers after that, then that works too. Okay? Now, some other terms. A one-to-one function. A function in which not only is there only one y for each x, that's the definition of a function, but there is also only one x for each y. Ooh. So not only does it pass the vertical line test, it will also pass the horizontal line test. So both vertical and horizontal. Pass both of them, it's called one-to-one. We also have this term called inverse, and remember this notation, f negative 1 of x. Then how do you find the inverse? Once again, you switch x and y and solve for y. Be careful here, and I want you to note only one-to-one functions have inverse functions. And since x and y are switched to produce these inverse functions, the domain of f really becomes the range of the inverse, and vice versa. And notice for coordinates on f, if a comma b is a coordinate on f, then of course you switch them, and b comma a is a coordinate on the inverse. So knowing that, can you tell me which examples in 1 to 4 are actually inverses or have inverses? Remember the idea of inverse? Both the vertical line test and horizontal line test must work. We know the vertical line test works for number 1, so does the horizontal. Ding! We know number 2, it's not even working for the vertical. No way. Notice for the number 3, the vertical works, yes, but the horizontal does not. And for number 4, the vertical already does not, so therefore the only one that's one-to-one is actually example number 1. Okay, because both the horizontal and vertical line tests are passed. Cool, cool. Number 13, how do we find the inverse now? Well, I just told you earlier, switch x and y, solve for the y. So remember, f of x is like y, so I'm going to switch that to x, and then the x, of course, becomes y. So after doing that first step of switching x and y, now you need to, that's right, solve for y. So first step was to, once again, isolate, oops, not isolate, my apologies, switch x and y. Step 2 now is to isolate the new y. So I'm going to move the 1 to the other side, divide both sides by 2, get rid of that cube by taking the cube root. Is there a plus or minus a cube root? Please say no, only the square root does, so it's just the cube root of x plus 1 all over, or all of x plus 1 all over 2. Now notice, because this is the inverse and it is a function, I know because a cubic is passes the vertical line test, and if I do that, I think this one also passes the horizontal line test. You can graph it out to double check. I can use this notation now. I can use the function notation. F inverse of x equals to the cube root of x plus 1 all over 2. Done. Whew. Okay, some of the concepts you'll see a lot in calculus, especially in Unit 1. Something called a piecewise function. Yes, hopefully you can see that this example here, wow, look at this, 3 different pieces. And hopefully you can see that with the graph, 3 different pieces. The first part is this graph of x, so y equals x, that's this 45-degree line. But it stops here at 0. Why? Because look, I've limited the domain to be x is less than or equal to 0. Because it's an equal sign, notice there's a solid dot. Now the next part here, 2 minus x, yes, that's the line with the y-intercept at 2. That's this part here. Notice why there's an open dot here at 2, because there is no x value at 0 being included. Okay? And similarly, this should be an open dot here, because this is less than, right? But because the last function, x squared, also shares that particular point before it becomes a parabolic curve, and that has an equal, that's why there's a solid dot there. So be careful with these solid dots. That means there's an equality, an open dot, and inequality, or just no equal sign. Okay, so 3 parts in the equation, 3 parts for the graph. So can you actually try number 14 now? Can you graph this piecewise function? And then also give the domain and range. So the absolute value of x, yeah, I hope you remember that's the V-shaped graph. Now, technically it goes like this, but wait. Notice the domain here, it only goes to 1. So this part's okay. And then I better stop here at 1. Open dot or solid dot right now? Open dot, good, because this is just less than 1. The next part I should do now is the equation x plus 2. So, oops, that is a line with a y-intercept of 2, and the line going up like this. Oops, what did I do wrong again? Don't forget, this only exists when x is greater or equal to 1, so I really should be looking at starting like this. Oh wait, don't even start on the y. Start right here and then move up. I believe that that should actually be a solid dot. And I better get rid of this solid dot here on the y-axis. I don't want that. This looks like a good graph. This definitely looks like the piecewise function. And if I'm looking for the domain, notice it exists at all values, even at 1, because even though there's a hole here, there's a solid dot up there. So all real numbers. All real numbers. And the range here, yes, it looks like we're looking at all the values that are greater or equal to 0. Good. All right. We talk about zeros. So what do I mean when I say zeros? Well, the zeros are really the x values where y equals to 0. We saw that in the previous lesson too. Conventionally, zeros are actually written as single values, so x equals to 2 or x equal to 5. Well, you can also classify zeros as x-intercepts, but x-intercepts are usually written as ordered pairs, so 2, 0 or 5, 0. So how do we find zeros without using a calculator? I've got a nice quadratic here. You could solve this using the quadratic formula if you want, or if you love factoring, that works as well. I think I'll try to factor. In this case, you're looking for 2 numbers multiplying to -4, and those same 2 numbers adding to -3. What combinations are possible? Figure out the one that works. Ding, ding, ding. You got it. Did you say 4 and 1? Wait, something has to be negative. Oh yes, -1. Good. And then, of course, then you can rewrite this as x plus. Good job. I hope you caught my mistake. remember here, I'm looking for negative 3. So if I made that negative 1, I'd have a big problem because 4 plus negative 1 is positive 3. So you need to change it to negative 4. And if you do that properly, look at this. It's x minus 4 in one bracket, x plus 1 in another bracket. And because you're finding the zeros and you want to make this y equal to 0, you have this. Two things multiplied by 0, meaning one of those things must be 0. X minus 4 equals 0, or x equals to 4. Ding, ding, ding. Answer. Or the other factor must equal to 0. X equals to negative 1. Ding, 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 ding. Similarly, please, number 16 here, I've got a fraction. If I want to make it equal to 0, I'm making y equal 0. Does the denominator really matter here? No, because if I multiply both sides by x squared plus 4, I'll still get 0 on the left, and I'll just have x squared minus 4 on the right. I'll factor this one again if you want, or if you don't want to factor, we can just isolate x and solve. Doesn't matter to me, but don't forget when you're square rooting exponent that is even, don't forget that's right, plus or minus. So here we have x equals to plus or minus 2. And by the way, sometimes this is why it's nicer if you can factor this, because if you factor this as x plus 2, x minus 2, a difference of squares, you automatically see, yes, there are two answers, x equals to negative 2 and x equals to positive 2. All right, the final part of this lovely review is on graphs. These are the graphs you should have memorized. Yes, did I say this right? Memorized from your pre-Calc 12 days. Maybe not these ones perhaps, but you should be familiar with them nonetheless. Okay? Definitely know these other ones. Okay? And what do I want to do with them? Well, you're going to have to do some graphing adjustments or transformations. Hopefully you remember all these different things from your pre-Calc 12 days. I'm not going to actually list them and read them out to you because I think you should know. Alright? The tricky ones are these ones down here, the absolute values, but nonetheless you should be okay with them. So take a moment to read this, please, and when you're done, I'm going to ask you to try the next examples, okay? And see if you can do them yourself first before actually me coming and showing you the work. Okay, this is review. I'm too fast? Yeah, I know. Read first. Pause the video if you need to. Read it, get used to it, and then do the questions. Thank you. So for these 5 examples, I want you to use the same function, okay? This one shown looks like a parabola and a line. Number 17 says, what does the graph of y equals f of x plus 2 then look like? Hopefully you can see that this x plus 2 represents a shifting of 2 to the left. So you're taking every single point and moving it 2 to the left. 1, 2. Okay, 1, 2. 1, 2. And then 1, 2, 1, 2. So hopefully you see this. Whee! Done. Okay. 18. What do we see here? This plus 2 outside the function means 2 up. This negative in front means a reflection in the good x-axis. So it's up to you which one you do first. I'm actually going to do the reflection first. Some of you may have learned the acronym BERT. I don't know if you did that or not, but B-E-R-T, start with the basic graph. E stands for your expansion compressions. R, of course, stands for your reflections. And then lastly, we do our T, translations, shifting left, right, up, down. So if I do the reflection first, notice the value here goes down there. Reflection on the x-axis stays the same. And then reflect, reflect, reflect. You're not done yet. You didn't do your 2 up. So now don't forget to go 2 up. And if you can do this all in one step, bravo. I'm just trying to show you all the steps so that you can understand. Doop, doop, doop. Done. Okay. Try 19 on your own. This is a vertical compression by a factor of 1/2. All the y values get squished. And then the negative with the x is a reflection in the y-axis. Good. So I'm going to go back. Oops. I'm going to go back, not that far back. I want to look at the graph again. Gotta do that vertical compression first. So instead of the value being at 2, it's going to be at 1. So you see how it's gotten flattened up a little bit? Flattened. And then you got to reflect it in the y-axis. So I'm going to do that in green. So reflect in the y-axis means this particular part now looks like that. And then the graph goes like this. Done. And there's your final answer. The one in green. Good. 20. Ooh, that 2 in the x, that's a horizontal compression by a factor of 1/2. This time I'm shrinking it horizontally, and then I'm putting the absolute value. So what happens with the absolute value? Do you remember? An absolute value outside actually does what? It, yes, reflects the points below the x-axis across to be above the x-axis, right? Because what you're saying is every negative value becomes positive, and so anything that's below the x-axis becomes positive. So let's quickly do the horizontal compression first. I'll do that in blue. So the horizontal compression, looking at my graph, not this point anymore, but I compressed it. So squish, squish. Okay, and then squish. Okay, and then now to do the absolute value portion, anything that is below the x-axis, these are the negative y values, get reflected to the top. So ultimately, only this part really changes. The rest of the graph here stays the same. Okay. Now maybe the trickiest one is this, where I'm taking the absolute value in the x. So what happens here? Let me try to illustrate this by actually using a table of values for the values from above. If I make a table of values here, -2, -1, 0, 1, 2. Notice I get 2, 0, 2, 1, 0, and I guess I should do one more, -1. When I show you the absolute value of x, what's going on? What I'm saying to you is, look, I want to now make the negative values reflect the positive x value. So really what I'm saying is get rid of these y values here, and I want you to figure out not f of -2, but the absolute value of -2, which actually becomes f of 2. Meaning, what is the corresponding y value when x equals to 2? And if you look at your chart, that means the answer is, yeah, it's actually right here. It's 0. And similarly here for -1, that means I want to find f of 1, and that's 1. So can you see how these values of -1 actually took on the same y values as +1? And can you see how -2 for x took on the same positive y value as +2? So really, what's going on here? Well, here's what's happening for number 21. You're eliminating all the points to the left of the y-axis, right? That's how I got rid of these. Goodbye, goodbye. And what did I replace it with? Well, you then replaced it with the what? The mirror image of the right part of the graph. Remember, I just took on those values, right? Became 1 and then 0. So you're just reflecting that. So really, everything to the right of the y-axis stayed the same. So no changes to these points here. But remember what we did was we got rid of this part. Goodbye! And we replaced it with, yes, the mirror image of the other side. And that is the graph you should have for number 21. Okay, lots of review, different topics, but nonetheless, listening is great, but doing is better. So now it's your turn to do.